Three threads are converging at once. The geometry of self-supervised vision is becoming mathematically legible. Predictive representation learning is getting more sample efficient, and LLMs are being stress tested on whether they can hold onto the truth when context turns deceptive. That matters because the next bottlenecks aren't just scale, they're inductive bias, robustness, and what a model actually does under pressure. Keep watching, because the details here explain why some systems learn cleaner features, why others fail in high-stakes settings, and what design choices are quietly moving the frontier. Let's explore the first paper, A Theory of Contrastive Learning with Natural Images. Antonio Torralba and Yair Weiss show that contrastive learning on natural images can be understood analytically through frequency domain statistics rather than heuristic invariances. By replacing InfoNCE with a Gaussian equivalent objective, they prove that the optimum is a partial whitening representation. It selects a subset of Fourier modes and rescales them inversely to expected power, so the embedding covariance becomes white. For simple augmentations such as circular crop, brightness, contrast jitter, and ideal blur, the globally optimal representation is just squared DFT magnitudes at k non-DC frequencies, normalized to a unit norm. This can be computed by a one hidden layer CNN with sinusoidal filters, pointwise nonlinearity, global average pooling, and a linear projection. For harder augmentations, including crop plus noise, arbitrary blur, and linear jitter, the optimal last layer weights are generalized eigenvectors of the alignment matrix B and covariance SE, with the selective frequencies found by a water-filling algorithm. The theory predicts, and experiments confirm, that SGD-trained CNNs on CFAR10, CFAR100, ImageNet, fractal noise, dead leaves, and Celeba learn sinusoidal first-layer filters and frequency sensitivities shaped like rings or diamonds in Fourier space. In their CFAR10 KNN study, training on non-CFAR synthetic noise yields the best transfer when its expected power spectrum matches CFAR10, reaching 45.1%, while simple partial whitening in PCA space gives 47.1% and close to the learned representation's performance. Let's explore the second paper, Measuring Epistemic Resilience of LLMs Under Misleading Medical Context. MedMisBench from the University of Oxford, University of Washington, University College London, and the University of Waterloo introduces a new evaluation target for medical LLMs, epistemic resilience, meaning whether a model preserves a correct medical judgment after plausible but false context is injected. The benchmark combines 10,932 answer-grounded medical questions drawn from MedQA, MedMCQA, MedExpertQA, MedJourney, and HLE with 48,889 misleading context option pairs spanning 5 corruption types and 3 provenance framings. Across 11 model configurations, clean accuracy averaged 71.1%, but focused. Type 1 injections dropped performance to 38% with 51.5% attack success rate, while Type 2 all-option delivery stayed near 70.5% accuracy, yet still produced 18.7% ASR. The most damaging attacks were rule-like fabrications. Authority-framed falsehoods reached 69.5%. Type 1 ASR exception poisoning reached 64.1%. And threshold reference corruption reached 60.9%. In clinician review by a 14-member panel from 7 countries, 38.2% of reviewed responses were worst-case outputs with serious potential harm. On mitigation, Gemini 3, one pro preview on HLE saw Type 1 ASR fall from 81.5% to 16.1% with search, while a defensive warning prompt reduced Type 1 ASR by 10.114 points, but did not remove the failure mode. Let's explore the third paper, Siam-JEPA, on the role of Siamese student encoders in JEPA. Siam-JEPA, from Makoto Yamada at the Okinawa Institute of Science and Technology, studies a simple but underexplored question in JEPA-style self-supervised vision learning. What happens if the student network uses Siamese encoders instead of a single encoder? The proposed model combines 2 independently masked Vite-based student branches with an exponential moving average teacher, a linear alignment predictor, and a probabilistic latent predictor inspired by finite and stochastic frame prediction. Training optimizes a masked latent prediction term plus a KL regularizer between a posterior inferred from both views and a prior inferred from one view, with disjoint masks used to prevent shortcut learning. On ImageNet linear probing, SIAM-JEPA reaches 70.2% top 1 accuracy after 400 epochs, compared with 61.9% for MAE at the same 400 epoch budget, while remaining close to CAE's 70.4% reached only after 1600 epochs. The original IJEPA baseline is reported at 72.9% after 600 epochs, but the setups are not directly comparable. The ablations show that the Siamese KL term acts mainly as a regularizer and accelerates early convergence. With KL weight 0.01, top 1 accuracy rises to 63.72% at epoch 169.3% at epoch 300 versus 57.89% and 66.78% for a much weaker 0.0001 setting. Block masking is consistently stronger than random masking, and larger weight decay improves the 400 epoch result to 70.15%, reinforcing the paper's core claim that Siamese student encoders are not just an architectural variant, but a useful inductive bias for predictive representation learning. That's a wrap on today's AI paper highlights. Thanks for watching.